All right, so this problem here, I wanted to go over a more challenging calorimetry problem with you guys, so you guys have something for reference. If you're wondering where this problem came from, it's the second page in your worksheet packet for specific heat and calorimetry number 2. And I'm going to be working out problem number 4 with you guys. And if I have a little more time, I'll squeeze in another problem for calorimetry. So we have some information here. We have an aluminum calorimeter and the specific heat of the calorimeter is given to us. We have a weight of the calorimeter. We know that we're dealing with some water that's inside of a calorimeter, and we also know the initial temperature of the water at 30 degrees. The final temperature here is 17 degrees, and then we're throwing in a piece of ice at -14 to the water, and we're trying to figure out what the weight of the ice is going to be in grams. Now, one of the things that I like to do before I start problems off like this is it's really helpful to kind of get a diagram in so you know what is going on and what is losing heat and what's gaining heat. So I'm just drawing in here. I have an aluminum calorimeter. We have some water that's placed into here. So let's write calorimeter. We have some water. And to this water, we're also throwing in a piece of ice, and this ice also has a temperature to it. So I want to start by recording out my initial temperature of everything so I could see whether heat was lost or gained. The calorimeter and the water, they both have a temperature at 30 degrees Celsius. And this part you guys want to be careful with. They only really mention the water being at 30 degrees Celsius, but the water is inside the calorimeter, so the temperature of the water will be the same as the calorimeter as well. So these guys here start at 30. Now the ice temperature is at -14, so you could see that it's not melting right away. It needs to warm up before it melts. And the final temperature of all three of these things here, right, we're being told that everything comes out to the same final temperature of 17 degrees Celsius. Okay, so looking at my problem here, we could see that the calorimeter and the water both dropped in heat. It got colder, whereas the ice went from -14 to 17 degrees Celsius, so we could see that it got hotter here. And anytime you see a problem like this where one thing gained heat and another thing lost heat, we know that they're going to be set equal to each other as Q lost, Q gained. So let's go ahead and fill this in. The things that lost heat, we have our calorimeter plus the water, and this is all equal to the ice over on the right side here, and that's the only object that gained heat. So for the calorimeter and the water, they're not dealing with any phase changes, they're just strict temperature changes here. So I know that it's MCAT for the calorimeter plus MCAT for the water, okay? And remember, the part where it's a little bit tricky is when we're dealing with ice, because ice could go through phase changes. So I have my heating curve of water here, and there's two temperatures you just want to be cognizant of. You have the 0 versus the 100 degrees at both points here. And the Q, or the starting temperature of the ice, it's at -14. So you could see it's going to go from -14 to 0. That's step 1. And then from here to here, the ice has to melt. Okay. And then it's not done. At 0 degrees, we know that the final temperature of this melted water is going to go up to 17 degrees. So step 3 is going from 0 to 17 degrees Celsius. Okay, so again, all three steps that we're checking out here, this is just for the ice, which we're going to put on the right side. And now you could go ahead and connect on equations to this. That and that are going to be MCATs because their temperature changes. And then for the second part, this is mass times the latent heat of fusion. Now, keep in mind here what's going on. This is from -14 to 0, the substance is still ice. It melted. So here for the third MCAT that we have, this is going to be water because it has melted. So you want to make sure you pick the right constants for these parts now. So I'm going to go through, let's add that part into the equation. We have the MCAT, and let's just say it's at ice, plus ML plus MCAT, again, at water. Okay, and you could see here that according to the problem, we're trying to figure out the weight of the ice. So this, and this are all going to be my unknowns. So I'm going to go ahead and just move my little thing here, and then I'm just going to flip over my paper so we have some space. Let's go ahead and fill in all the variables here and solve for whatever we were looking for. So the mass of the calorimeter was 53.6 grams. The specific heat of the calorimeter was 0.215 calories over grams degrees Celsius. And the temperature change for the calorimeter, we started at 30 to 17, so there was a degree difference of 13 degrees Celsius. And we're going to go ahead and add on the water. We have 38.9 grams of water. The specific heat of water is 1 cal over grams degrees Celsius. And the temperature change of the water, again, from 30 to 17, so it changed by 13 degrees Celsius. Okay, so let's move all this here. Now, let's go ahead and handle the ice side. So we have MCAT for the ice. Remember the M we don't know for the ice. We don't know the weight. The specific heat constant for ice is cals, or 0.52 calories per grams degrees Celsius. The temperature change of the ice in part 1 was from -14 to 0, so it's 14 degrees Celsius. Mass, again, I don't know. The latent heat of fusion for ice for melting is 80 cals per gram. And to finish us off with MCAT for the water, the M, I don't know. The specific heat constant is 1 cals over grams degrees Celsius. And the temperature change for the water went from 0 to a final temperature of 17. So we have 17 degrees Celsius. Okay, so if you go through and we take the time to multiply everything over on the left side, and let me go grab a calculator for this. And then I multiplied everything on the left to get 65 or 655.512. I simplified these here, so I have 3 different values of M, so we're going to just add those up. So 7.28 plus 80 plus 17, and we wind up with 104.28 times M. And then on the right side, you have 655.512. We're going to divide both sides by the number on the right. So that cancels. And then for the final mass of the ice, I got 6.28607. And you just want to go through the main problem and again check out how many significant figures we need in our problem. I'm going to go with the smallest number of sig figs given. So I have 3, 3, 2, and 3, and 3. So I'm going to just round this off to 2 sig figs and get it to 6.3 grams is my final answer for that problem. Okay. And let me go ahead and try this problem here as well for number 2. So it says how many grams of ice at 0 are needed to drop the temperature of 100 grams of water by 35 degrees Celsius. Oh, actually, this is the problem that how'd you guys skip over? So let me go ahead and check out number 3 with you guys right here. It says, what mass of ice will absorb 385 kilojoules? So this is my Q, or energy, if the temperature is raised from -25 or -21 to 25 degrees Celsius. And again, we're solving for M. Okay, so here, you're not dealing with a scenario like we did back for problem 4, where we had a calorimeter, we had water, and we had ice. This problem is a lot more simplified in that we're just dealing with one object, which is the mass. And you know that temperature is being raised, so it's -21 to 25. And this is just going to be a problem where you figure out the total heat or total energy for everything. But since we're dealing with ice, we know that we're going to be dealing with the ice going into various steps. So let me draw that over here with you guys. We have, again, our heating curve for the ice. This is my 0, this is my 100, and we're going from -21 to 25. So I'm starting here. Here's step 1. We're going from -21 to 0. Okay. Step 2 is from 0 to here. This is the melting phase of the ice. Okay. And then the third part of this is from 0 to 25. So we have 0 degrees to 25 degrees here. So we know that this is going to be MCAT here, ML here, and then MCAT over here. So let's plug that in. We have MCAT, and remember this is MCAT for ice. We have ml here, and this is because the ice is melting when it hits 0. And then we have another MCAT here, and this is when we're dealing with the ice having melted, so we're looking at water. Okay, and really similar to that last problem that I did, which I thought was more challenging, you have a mass that you're solving for, which means we need to know what the total heat was for this mass of ice to go through all these different steps. Now in the problem, you guys, I remember, initially had trouble with this one because of the units that were provided for you guys. You were given kilojoules here, and in your notes, you do have some specific heat constants, like for the ice and for the water, given to you in joules per grams degree Celsius, which is easy enough to use. But the latent heat of fusion that's given to you, the other one, you guys had 80 calories per gram, but the other one is a unit given to you in kilojoules per mole, not kilojoules per gram. So you actually do not want to try to use kilojoules for my heat here. It's actually a lot easier to convert this straight over into calories. And then we're going to use 0.52, 80, and then 1 for these constants. And then at the end, once you have calories, you're good. And the thing you just want to remember is if you're plugging in an ice problem and it involves melting or condensation or vaporization and you have a L constant, really good idea to change kilojoules out into calories right away, because if you don't do that, you actually have to change your mass into moles, and that makes it a little more complicated. So let me just walk you through the conversion. 385 kilojoules is 3 decimal places to the right. That's that many joules. And there in 1 calorie, it's equal to 4.184 joules. And this is a conversion you guys don't have to memorize. You would get for the test. So we're just going to divide that really quickly. And I got 9,200 or 92,017. And that's how many calories we're going to be dealing with in the problem. And I didn't round it because I want to round it at the very end. So let's go ahead and start setting up. I'm going to put this number in for my Q total here. And it's equal to mass. So the rest of the setup is just very similar to what you guys have already done. I don't know the mass. I know that my constant is 0.52 for the ice. The temperature change for the ice is from -21 to 0. Don't do -21 to 25. You have to break it down into 3 steps. So this is 21 degrees Celsius. Then the mass of the ice times 80 calories per gram, right? And then you have the mass of the water times 1 cal per grams degrees Celsius. And the temperature change, again, is from 0 to 25. Ooh, and I'm going to run out of time on this video, so I'm going to speed things up a little bit. So let me go ahead and give you guys the calculated numbers for this. So when you go through and simplify the right side, you end up with 3 m values here, which we're going to add up. We get 115.92, and then we're going to divide 92,017.208 divided by, and then that will lead us to our final answer of let's see. 793.799 grams, but looking at the problem, smallest number of sig figs I see is 3, so we're going to round this to 794 grams of ice. And that's it. And we have such a big number this time because you're dealing with 385 kilojoules of energy, which is a lot bigger than joules. So hopefully this video kind of helped you guys to make sense of some of these tougher calorimetry problems.